Hello, everyone. This is Dr. Sami again from the Biostatistics Learning Group. And here we'll talk about the correlation coefficient or correlation. So the correlation coefficient has a strange sampling distribution, but the quantity T calculated from the observed correlation coefficient R based on the number of observations by the formula. So T, we mentioned the quantity equals R, the correlation coefficient, divided by 1 minus R square divided by N minus 2. So it fluctuates in accordance with the student T distribution, with N minus 2 is the degrees of freedom, df. You can get a p-value from a t-value by going to a table of the student T distribution or by using an online calculator. For example, if R equals 0.500 for a sample of 12 subjects, then T equals 0.5 divided by the square root of 1 minus 0.5 square divided by 12 minus 2, which works out to T equals 1.8. So with 10 degrees of freedom, as mentioned, that degree of freedom is N minus 2. So using the stat pages info with page and entering the T and TD value, you get a p-value of 0.09, which is a statistically significant, which is greater than, it's larger than 0.05, so it's statistically non-significant because the 9.09 is larger than 0.05. So it's a greater than 0.05, so the R value of 0.500 is not statistically different from 0. Over the years, B minus or equal to 0.05 has become accepted as a reasonable criterion for declaring significance. So how precise is an R value? You can calculate confidence limits around an observed R value using a somewhat roundabout process. The quantity Z calculated by the Fisher Z transformation is approximately normally distributed with a standard deviation. So the Z equals half log, then 1 plus R over 1 minus R. It's approximately normally distributed with a standard deviation of 1 divided by the square root of N minus 3. So the formula for normal-based confidence intervals, you can calculate the low and high confidence intervals. So using the example from the preceding section of R equals 0.500 for a sample of 12 subjects, you can perform the following steps. First is to calculate the Fisher Z transformation of the observed R values. And that would be half log 1 plus 0.5 divided by 1 minus 0.5. Calculate the low and high 95% confidence interval limits for Z, Z low, Z high. Z low is where you subtract it by 1.96 and Z high is you add to it 1.96 as it's mentioned there. So you add to it, and then you divide it by the number of subjects, which is n minus 3, and then you get the different results. As this is Z low, Z high. So calculate the low and high 95% confidence intervals for R. And R low, R high is as here E squared multiply by, and then you follow the formula. So notice the 95% confidence interval goes from minus 0.104 to plus 0.835. Right. It's a range that includes the value 0. So this means that the true R value could indeed be 0, which is consistent with the non-significant p-value of 0.09 that obtained from the significant test of R in the preceding section. So if the confidence interval involves 0, then it is statistically non-significant. So R2 values, R2 R values significantly different. And then you go through the same formulas. So what is the required sample size for a correlation test? So if you're planning a study whose main purpose is to determine whether two variables, X and Y, are significantly correlated, you want to make sure that you have a large enough sample size to give you a good chance of showing significance, which is about the power. So to perform a sample size calculation, you need to specify 3 things, which are called the design parameters of the study, which is the alpha level of the test, the desired power of the test, and the effect size of importance. So the alpha level of the test is the p-value that considers significant when you are testing the correlation coefficient. Usually this is set to 0.05, unless you have special considerations. The desired power of the test, the probability that the regression comes out significant, often this is set to 80% or 0.8. The effect size of the importance, the smaller R value that you consider worth knowing about. If the true R is less than this value, then you don't care whether the test comes out significant. But if R is greater than this value, you want a significant result. So I can't tell you what value of R is worth knowing about. It depends on your research goals. If you're hoping to be able to estimate Y from a known value of X, then R has to be fairly high, perhaps 80%, 0.8 or higher. But in more pure science applications, we're trying to discover cause and effect relationships in biological systems. You may be interested in knowing about even weak associations, like R is 0.1 correlation coefficient or 0.2. Figure 17.1 help choose the R value that's worth knowing about for your study. And that is the figure 17.1 he is talking about. And we mentioned that it's plus 1 or minus 1 if the points lie along a straight line. And that is when the relationship is perfect. And it's screwed like there is no relationship if the points scatter all over the place. And R would be around 0, right? So it could not be like specifically 0, but around it. So 0.5, 0.8, and so forth. Thank you so much. By this, we conclude our session.